Do you remember 2 lectures ago, I talked about, at the end, about 3-dimensional rigidity in higher dimensions and showed these examples like the double bananas, where a graph that is d-tied, but it's not minimally rigid or not rigid in d-dimensional space. I want to do similar things today in terms of telling you about higher than 2 dimensions, but I want to tell you sort of the good direction. So classes of graphs for which we do understand rigidity, in particular classes of graphs for which the d-tight condition is sufficient to guarantee d-rigidity. And so we'll focus on 3 dimensions. And then an advert that on Wednesday, Sean Dewar will give the lecture in this course, and he will talk about complete bipartite graphs. So complete bipartite graphs is one class of graphs where we do understand a lot in d-dimensional rigidity. And the first class of graphs I'm really going to talk about today are triangulations, and they're another class where we have a really good understanding. And then in between those 2 classes, there is lots of complicated things that can happen. Okay, so as I say, we're going to talk about rigidity when d is greater than or equal to 2. Yes, it is recording, I believe. Thanks, William. So a simple observation to get started is that we can check small graphs by hand. We can just calculate the rank of the rigidity matrix. So for example, K4, complete graph from 4 vertices, is a free-type graph, which we can easily check has the right rank of the rigidity matrix to be rigid in 3 dimensions. And we've already seen that the 0 extension operation and the 1 extension operation, and then 2 lectures ago, we talked about vertex splitting. So we know certain operations preserve rigidity in 3 dimensions. So we can use the 3-dimensional versions of these 3 operations to generate many, many examples of free-type graphs that are minimally rigid. So sort of, in some sense, typical graph that is free type will be rigid, because you can get lots and lots of such graphs for these operations. And so one exercise, if you like, and this is kind of open-ended because I don't really know what the answer is in nice closed form, but try and understand what graphs you actually get just from these operations, and try and give some sort of understanding of what you get, and think about what graphs you can't get. So it's easier to decide particular graphs that are free type that you can't get from these operations, because you can look at the minimum degree, you can look at the girth of the graph, for example, but understanding what the class of graphs you get from these operations, I think would be a nice thing to do if anyone wants an open-ended exercise. Okay, so as I said, I want to talk about triangulations. So in particular, there's a really general result, which I won't go into, but it's a really nice result obtained by Vogelsanger in the 80s. And what he did, essentially, he proved that you take any surface you like, any closed 2-dimensional manifold with no boundary, and you triangulate that surface. What you get is the graph of the triangulation is rigid in 3-dimensional space. And so there's a couple of comments to make here. So first of all, the triangulation of the surface itself, the topology you get, doesn't play any real role in the rigidity. So all I really mean by saying the graph of a triangulation of a surface is rigid is that the triangulation of the surface gives me a graph, the graph of that triangulation, and then I take that graph and I realize it generically in 3-dimensional Euclidean space, and then I ask if that graph generically realized is rigid, and Vogelsanger proves that it always is. Okay.
Tony?
Yes.
Okay, go ahead, Al.
Oh, sorry. You wrote arbitrary, but then you said it closed without boundary.
Yeah, by arbitrary, I meant arbitrary genus, I guess. So orientable or non-orientable genus, whatever you like. But I don't want to worry about ones with boundaries.
Okay.
Yeah, so maybe arbitrary was a bit misleading, sorry.
And does the surface have to be embeddable in R3 or not?
I'd have to check Vogelsanger's proof, but I think that's the context he was working, yes.
Okay, cool.
I'm not 100% sure on that, though.
So you could take the Klein bottle immersed in R3, triangulate it, and see? if
Yeah.
it's rigid. Okay, but that's not covered by this.
Yeah, to be honest, I'm not 100% sure of the exact generality that Vogel-Sanger did it, but I mean, I bet the answer is true, is that it is rigid, but whether it was quite covered by his theorem or not, I'm not 100% sure.
I think yes. I think that
I think it is covered.
that complete that was talking about all surfaces, oriented, non-oriented, was giving just rigidity, non-minimal rigidity.
Yes. Okay, so let's just think about the count. So we're in three-dimensional space. So the d-type count tells us that the number of edges should be 3v minus 6. But it's easy to check using the Euler's formula what the number of edges you will get in a triangulation of a surface depending on the genus. And as long as it's not the sphere, it's definitely going to be more than 3v minus 6. So Vogel-Sanger's result, if the genus is high, it tells you rigidity, but it doesn't really tell you anything about minimal rigidity, because you can have many, many more edges than you need for the minimal rigidity count. And it doesn't tell you anything about how you would delete edges to find a basis, to find a base in the matroid, or to find a minimally rigid spanning subgraph. So I can point out that Lev Terrace, who made a comment just now, and Steve Power, and Jim Cruikshank, and Derek Kitson, and previously Walter Whiteley and Alyssa Ross and Wendy Fimbo Singh, several groups of people have started looking at taking triangulations of surfaces that aren't the sphere and then cutting out some edges, making some holes or adding some edges in, and trying to head towards a more minimal rigidity kind of result for specific small genus surfaces. I don't want to say anything more really about arbitrary surfaces. I just mentioned this generality to really focus on triangulations of the sphere, just planar graphs, and in particular maximal planar graphs. So what we're going to show is that every planar graph is independent in the three-dimensional rigidity matroid. And the way we're going to do it is by showing that maximal planar graphs in which adding any edge will destroy the planarity, are exactly or minimally rigid. So that they're 3v minus 6 graphs that happen to be minimally rigid and provably minimally rigid. Okay. So again, it is not a difficult exercise to show that every maximal planar graph has 3v minus 6 edges. You can also show they're all free connected. You show that every face in the graph is a triangle. There's several easy properties of maximal planar graphs that are sort of relevant, but I'm just going to take them all for granted. And our proof is really going to be very short. It's going to be the consequence of what we've already talked about with vertex splitting and this proposition that's here. So remember 2 lectures ago, we were doing vertex splitting in 2D, and we had to care about when you split. So in 2D, you had this move where you took U and you split it into U dash and U double dash, say, and V went to here. And you had to care about how the edges over here were split amongst these 2 vertices, because you might destroy planarity if you don't. So you have exactly the same condition in 3D when your vertex split really has a W here and a second vertex split into 2. So in the 3-dimensional case, for example, when you're doing reductions, you want to pick 2 edge-sharing triangles where the 2 triangles are both faces, and contract that edge that was common to the 2 triangles and go down. And when you're doing the extension, you have to be careful with how you apply how you mix the edges instant to U with edges instant to U dash and U double dash. But you can do that, and I won't go into any more detail with that. And so let me just say the proposition and then really the rigidity corollary. So Steinitz and Rademacher proved that every maximal planar graph can be obtained from K4 by vertex splitting operations. So they showed in any maximal planar graph, you have 2 edge sharing triangles like this, and you can contract an edge, and you can contract most edges in a maximal planar graph. Okay, so then Gluck's theorem, although I wasn't quite sure who to reference here, so someone might shout if they think I should have appropriated this to someone else, but I'm assigning it to Gluck for now. He proved that every maximal planar graph, equivalently every triangulation of the sphere, is minimally rigid in three-dimensional space. Gluck's proof, I'm not going to present. I'm going to present a sort of a 4-line proof, which is basically a corollary to the theorem the proposition we just had, and the theorem of Whiteley we had a couple of lectures ago on vertex splitting. So it's a very simple inductive argument. We already talked about K4 being rigid in 3 dimensions. That's the basis of our construction, and vertex splitting preserves rigidity. That's Walter's theorem, and the proposition says every maximal planar graph is obtained from K4 by vertex splittings. So this is a very simple induction argument. And there's a question. Can we not get triangulations from K2 and 0 extensions? Yeah, so what I wanted to start with was a 3-6 type graph with E equals 3b minus 6. So K2 is a weird graph because it has the wrong count, and so you sort of ignore it when it's a subgraph of things. So I don't want to start there. And then I guess, as Sean says, if you're just doing 0 extensions, well, if you're doing 3-dimensional 0 extensions on a triangle, you can get K4. So maybe yeah, okay. It seems that William's happy with my answer. Daniel says, are the set of all planar graphs the independent sets of a metroid? I hadn't thought of that before. A subset of a planar graph is still planar. So you want to do the swapping axiom, I guess, if you want to check the independent sets. Maybe someone knows the answer to this and can answer Daniel in the chat. Probably. You take 2 planar graphs of different sizes. Is there something in one you can add to the other? I'll let someone else either answer that, or Daniel, I can talk about it with you if you like afterwards. So this is saying that planar graphs are nice. And so in particular, if you have a free type graph, which is not free rigid, then it contains a non-planar subgraph. So that's sort of an interesting topological aspect to where the bad problems are in 3-dimensional rigidity. And I thought it's nice to extend this. And so this is kind of a result that I think is not as well known as maybe it should be, because it's a improvement on the result we just said. So Erin Navo proved that K5 minor free graphs are actually all independent in the 3-dimensional rigidity metroid as well. So we've just shown that every planar graph is independent. And remember that, so actually maybe I should first remind, in case anyone doesn't know, if you have a graph G, then another graph H is called a minor of G if you can obtain H from G by 3 operations. You're allowed to delete edges, you're allowed to delete isolated vertices, and you're allowed to contract edges. So for example, any subgraph is a minor of a graph, but also you can have a minor like a triangle lives inside C4. So this is not, minors is not usually something that's so related to rigidity, because obviously in 2D, this one is rigid, this one is flexible. So one's a minor of the other, so it can change. But minors are definitely related to planar graphs because of Kuratowski's theorem. So Kuratowski showed that a graph is planar if and only if it has no K5 and no K3 minor. And so the result of Gluck that we just talked about is saying that every graph with no K5 or K3 minor is independent in the 3-dimensional rigidity metroid. And Navo basically showed that you can delete this part. So you can just say you have no K5 minor. So you widen your class of graphs to include things like K3. Okay, so I do want to go through how Navo did his proof, but the thing that I guess is more interesting to me about is not just that the extension, but that K5 minor free graphs you can naturally think of a similar question in arbitrary dimension. You could think of KD+2 minor free graphs in RD, whereas planar graphs don't easily generalize to our arbitrary dimension. Okay, so I'm going to use vertex splitting in the proof as Navo did. So I need one thing to to say about the vertex splitting operation. So what we did, so here's a three-dimensional vertex split again. So this was, say, U, and this is U dash and U double dash that's split into. So this operation, Walter Whiteley showed, preserves rigidity, but it also preserves independence. It preserves minimal rigidity, but it still preserves independence if I take away some of the edges here. So if I only did, say, that, it would still preserve independence because it preserved minimal rigidity with that edge. So throw the edge away, they're still linearly independent rows. So these edges that I put in the middle, I could have less than all of them if I wanted to. So that's what I say in this paragraph. So instead of splitting, I've called it X here, sorry, and joining the two new vertices to D-1 common neighbors, we can join them to at most D-1 common neighbors. So as I say, we don't preserve rigidity anymore unless the at most is actually equal to, but we still do preserve independence. Okay, so let's prove Nevo's theorem. So he showed that every K5 minor free graph is independent in 3 dimensions. Okay, so suppose I give you a graph with no K5 minor. If G contains an edge E in at most 2 triangles, then we can do a contraction of that edge E. Here it's in 2 triangles, but it could be in at most. We contract E. That's one of the operations in your definition of what a minor is. So we know that if this has no K5 minor, then the graph we get from contracting E will have no K5 minor. So we're still in the same class. So if G contains an edge in at most 2 triangles, then G contract E is K5 minor 3, and obviously it has less vertices. So we're set up to do an induction argument. So the fact that vertex splitting preserves rigidity, and this version where we don't have some of these edges may not exist, then preserves independence. So we'll be done by induction. So all we have to do to prove the theorem is show that G contains an edge E in at most 2 triangles. So as soon as we've done that, we'll be done just by the properties of minors and the vertex splitting theorem. Okay, so how do we show that G contains an edge in at most 2 triangles? And this must be, this is the hard part, but it's also the part that goes wrong in higher dimensions. So it is worth checking why it's true. So let's go through that in a bit of detail. We're going to need one theorem. So the theorem we'll make use of is due to Mader in 1968. So he proved that if a graph has no KT plus 2 minor, then the edges are at most exactly what you expect in the D-type count. So we know if G has no K5 minor, then E is at most 3V minus 6. So we're definitely all sparse, so we have a chance. But actually, he showed this, so I haven't written it here. He did not show this in general. So this is not true in general. So it's true when T is less than or equal to, oh, there might be a lower bound as well, but don't worry about the lower bound because we only really care about dimensions 3 and up. So we'll assume T is at least 1. Yeah, so if it no K3 minor is E is at most 1V minus 1, so that's fine. But the upper bound, I believe it works up to T is 5. It might be 4. So this number here is either 5 or 4. And we could look it up quickly, but I just forgot to note it down. So it definitely doesn't work for K8 minor 3 graphs. I've forgotten if it works for K7. But it definitely works for K5 and K6 minor 3 graphs. Okay. Anyway, so let me continue.
So I have a question real quick.
Yeah.
That's okay. So is this basically saying that if you don't have a T plus 2 minor, then you're independent in some sparsity matroid?
Well, so it's the D comma D plus 1 choose 2 sparsity, which is not matroidal, but
oh, right.
Yeah, you're independent. You're sparse in this count sense. Yes.
Okay.
So if you just change this number so you are in the matroidal range, that will have even more edges. So yeah, you would be independent in that sparsity matroid. Yes.
Okay. Thanks.
I guess I can say while we're here that this result is nice for these small values, modulo me forgetting quite which one it fixes at. But if I take t to be large, then this result is very far from true. So for t large enough, you can have random graphs where the number of edges is more like, average degree is more like 2t rather than what we get here. So the average degree can be quite a lot bigger than the count here. So it's no chance of being true generally. Okay, so
Hey, Tony.
yes.
Sorry. Can you explain what sparsity matroid means?
Okay.
In your answer, you mentioned that.
Yeah, so let's see if this, yeah, okay, good. So we have a little bit of space. So let's say E is equal to KV minus L. So K and L are natural numbers, and 0 is less than L is less than 2K. And let's say I of X is at most KX minus L for all X in V, such that X is size at least K. So this is the definition of a KL tight graph. So it's a graph with this count, such that this sparsity condition happens for all subsets of the vertex set. That's a KL tight graph. It's for this range of natural numbers L and K, these are the bases of a matroid on the complete graph. So you can think of the independence condition as being this sparsity condition, and then the bases also have this equality. But you notice that, say in 3D, you'd want 3v minus 6, and this fails. So you don't quite get a nice matroid all the time, but you do within this sort of sparsity range.
Oh, okay. That was really helpful. Thank you.
Okay. So I guess in this course, the K will always be D and the L will always be this thing. So it's not in the nice matroidal range, but they are, except when D is 1 and 2, but they are nice, nice graphs. Okay, so remember what we're trying to do. We're taking a K5 minor 3 graph, and we want to show that there is an edge in at most 2 triangles. So the use of Mader's theorem, we're going to use it twice. The first is because it tells us that E is at most 3v minus 6. We can apply the handshaking lemma to imply that that guarantees us a vertex of degree at most 5. The average degree is close to 6, but because of this minus, it's strictly less than 6, so that must have a minimum degree at most 5. Now, we want to show that there's an edge in at most 2 triangles, so we're going to suppose that every edge belongs to at least 3 triangles and find a contradiction. Now, contradiction will be to show that G has a K5 minor. Okay, so pick a vertex of minimum degree. Now let's look straight to here. So I pick a vertex U of minimum degree. Every edge incident to U, in fact, every edge in the graph is in at least 3 triangles. So if I pick an edge E, it's in 1 triangle, 2 triangles, 3 triangles. So that already says there's 4 incident edges here. So we know the degree is at least 4, minimum degree vertex is at least 4, and it's at most 5 from before. So we have 2 cases to deal with if U has degree 4 or degree 5. Suppose it has degree 4, then I can just keep looking at this picture. Now, it's true that every edge is in at least 3 triangles. So pick an edge incident to U that I haven't picked, not E. So if I look at this F, then it must be in 3 triangles. But if it was in a triangle that went to some other vertex other than the 5 I've drawn, then that would give another edge to U and would contradict the fact that U was degree 4. So it must be that F has some edge to some other vertex in here, which creates a second triangle, and some edge to another vertex in here, which creates a third triangle. So that gives me the 2 blue edges, you can see. And then you can play the same game again on another edge. So let's take G, and that forces the edge to this one, and you get K5. But K5 is clearly not possible in a K5 minor 3 graph, so we're done in the case when the degree of U was 4. Okay?
Why did the second red edge have to go to U?
Second red, oh, so it doesn't. So over here, so what I said was this F here has to be in at least 3 triangles, that's our assumption. So this edge has to be in a triangle, which means it has to be this vertex, and some other vertex that are all at edges. So either it looks like that, or these two didn't exist and it looks like that, or it looks like that. So
Okay.
if it went to some other vertex outside that I've scribbled out, then the degree of U would go higher. So it has to be the other case, and it gives me the blue edges like this. Is that okay?
Yeah, that makes sense. Thanks.
Thanks. Okay, so that's what happens if the degree was 4. You get this K5 just as a subgraph, and it just sits there. Hence, we can assume that our minimum degree vertex has degree 5. So it's got 5 neighbors, X, Y, Z, W, V, say. Pick one of them arbitrarily. We know the edge between them, this edge UX, is in at least 3 triangles. For the same reason as what we just talked about with Alex, it can't be that there's a triangle like this. So the triangles must include 3 of the vertices Y, Z, W, V. So X has at least 3 neighbors in this set, but X was arbitrary among those 5 vertices. So the number of edges induced by X, Y, Z, W, and V is at least 3 for each of the 5, so 3 times 5, but I've double counted, so I divide by 2. But obviously I have to round up to get a natural number. So what I get is that there must be at least 8 edges on that 5 vertex subgraph on the neighbors of U. But on the other hand, we'll show that there can't be 8. So the other hand, we use the minor property. So suppose you had a K4 minor on the vertices X, Y, Z, V, W, then all 5 of them are adjacent to U. So the K4 minor on that subset would give us a K5 minor when we include U. So we know there can be no K4 minor on the neighbors of U. And so we can apply Mader's result from before about K4 minors. So that's the case when T equaled 2 in there. So we said if there's no K4 minors at most 2V minus 3 edges, to say that the number of edges induced by the neighbors is at most 2V minus 3. But 2V minus 3 when V is 5 is 7. And we just found it had to be at least 8 if there were at least 3 triangles per edge. So we've got a contradiction, and the contradiction tells us there's an edge in most 2 triangles, and hence we can apply the simple inductive argument and Whiteley's vertex splitting, and we've completed the proof. Okay, any questions on that proof?
Can you scroll back up to Mader's result?
Yes, here it is. So it's been scribbled all over, but it says if G has no KT plus 2 minor, and T is in some range, then the number of edges is at most T mod V minus T plus 1 choose 2.
Okay, thanks.
Okay, so let me briefly remark that Nevo didn't just prove a 3-dimensional result, he also looked at K6 minor free graphs in R4. And it occurs to me that this is telling me what the bounded Mader's theorem must be, because I also say here that Albar and Gonsalves in 2017, they dealt with K7 minor free graphs in R5. So K7 minor free graphs must be okay. So that tells us what the T was above. But in general, and so Albar and Gonsalves work on K8 minor free graphs, and they show that there's some nice structure to them. But these graphs don't have to be sparse, so it's harder to work out which ones are independent. So it's harder to work out when the sparsity condition gives you independence more generally. So and by the way, both Nevo's proof in R4, it used the same idea, but it was a bit harder, and Albar and Gonsalves did some computer assistance, and so theirs was a bit tricky to prove. So it doesn't continue to be as easy as the proof I explained. Okay, so the third and final main aim of this lecture is to give another characterization, but this time for graphs where we control a degree in a certain way. So this time I'm not going to be talking about rigidity, I'm going to be talking about independence. Okay, so this is due to Bill Jackson and Tibor Jordan in 2005. They proved that a connected graph, and the word connected is important here, with maximum degree at most d plus 2 and minimum degree at most d plus 1, if such a graph is independent in the d-dimensional rigidity matroid, if and only if it's d-sparse. So they showed that the double banana kind of things can't happen if your degrees are nice, so the degrees are quite small. Notice that this is not a rigidity result. So I said this already, but if you're D tight, then the average degree is close to 2D. And so saying all the vertices have these degrees, if you were D tight, would tell you you were a very, very small graph. But because they're interested in independence and sparsity, you can have as many vertices as you like, as long as they're quite small degrees. The one key point here, as I said, was the word connected, because it is an open problem to extend this to improve the minimum degree to D plus 2. So if you want to replace D plus 1 with D plus 2, then that seems to be challenging. And the reason why connected is needed is for that reason, I think. So if you were disconnected, you could imagine you satisfied all the other conditions by having a D plus 2 regular graph here and a graph here with a vertex of degree D plus 1. And then you'd have to understand the complication of this component to get anywhere. So they need the word connected in there. Okay, so hopefully the theorem is understandable. For the proof, I want just to make things a little bit easier notationally, but I'm not making any simplification in terms of the actual proof technique. It's just for notation. I'm going to focus only on the case when D equals 3. So what does their theorem say in dimension 3? It says if you're a connected graph with maximum degree at most 5, minimum degree at most 4, then independent if and only if free sparse. Okay, so we know that independent graphs in the 3D rigidity matroid are free sparse, so all we have to do is look at the sufficiency, but it'll need a couple of lemmas to do this. I think I've got 2 easy lemmas and 1 non-trivial lemma to make this theorem work. Okay, so you might remember when we were talking about Lemann's theorem, we had critical sets. So we have the 3-dimensional version of critical sets. So this is a subset of the vertex set that either it's a small complete graph, so either it's K2, K3, or K4, or it's a set on at least 5 vertices with I of x is 3x minus 6. So these are basically the sets of vertices that induce tight subgraphs of your sparse graph. Okay. Yeah, and I guess just in case anyone's confused, if you take the size of x to be 3 or 4, then you satisfy both terms in the definition. So I could have just talked about K2s here, but this was because they worked with general dimension D, it was easier. Just what they did was this split, and so I just kept the same notation as in the paper. Okay. So what we care about, we know the minimum degree is at most 4. If there's a vertex of degree at most 3, we can do 0 reductions, or we can add edges and do 0 reductions. And so they're kind of easy. So what we really want to worry about is vertices of degree exactly 4. So suppose V is such a vertex, then we're going to think about 1 reductions at V. So remember, this is, we delete the vertex V and add 1 edge among the 4 neighbors of V. And if we delete V and add the edge xy, then we're going to use G sub V superscript xy to denote the resulting graph. And if we do a 1 reduction at V in a free sparse graph G, then the 1 reduction, we call it admissible if this graph GVXY is also free sparse. Okay, so this is admissible is when the 1 reduction actually worked and kept us within the class of free sparse graphs that we want to be in. So we're going to look for admissible 1 reductions. Okay, so here's a lemma that I'm not going to prove, but it's basically the same argument as we talked about in the 2-dimensional case. So a 1 reduction at V, adding an edge xy, is non-admissible if and only if there is a critical set where the end vertices of the edge we want to add are already present in x minus V. So what we're doing, we're saying, here's our vertex V, here's x, y, and say the other neighbors are ZW. If the edge was already there, i.e. this was the complete graph, one of the complete graph cases, then clearly we can't reduce V and add xy because we'll have parallel edges. So let's suppose this edge is not there. Then we need to break the sparsity condition. So there must be a critical set. And this time it's a bit more complicated than in the 2D version, because in the 2D version, when we were reducing V and we added an edge, we knew that if it was blocking xy, it did not contain the third neighbor Z. But this time it could contain one of the neighbors Z or W. So I'm not going to loop it around. It could contain Z, it could contain W. It can't contain both, as we'll see, but it could contain one of the two. So there's a bit of an extra complication there.
Does it contain V? Because you write X minus V.
Yeah, so it doesn't contain V. So the critical set lives inside basically it lives inside this smaller graph, because it's, when we delete V goes away and we add the edge in, then it causes the problem. So the critical set lives in G, but it lives in this part of G because it's what's going to affect the graph where you've not got V anymore. So yes, it definitely should be an X minus V. Okay, so here's a lemma, and this is really a very simple lemma, but this is the reason that the degree is going to help us, because we can apply this. So if I take a critical set in a free sparse graph, and let's suppose we're taking a critical set with 3v minus 6 edges, not a complete one, then the degree of every vertex in X is at least 3 in the subgraph induced by X. So X is a free type graph itself, so its minimum degree is 3, so every vertex in it has degree at least 3. So that's easy, but I'll just do a very short proof anyway. And this is going to be useful because we have maximum degree 5. So you can imagine it doesn't take much to turn a degree 3 vertex into a degree 6 by looking what else is incident to it in G outside of G induced by X, to find the extra vertices that help you to get a contradiction. And that's what we're going to do in a bit. Okay, so suppose we have a critical set and there's a vertex whose degree in that induced by that critical set is less than 3. Then we know that I of X is 3x minus 6, so we just work out what I of X minus X is. Well, it's equal to the number of edges in X minus the number of edges incident to X. I of X is 3x minus 6, so this just comes along. But since this is strictly less than 3, when we move from X to X minus X and take this away, we get a strict inequality, and we have a contradiction of sparsity because we have this set X minus X with too many edges in it. So this is just a very quick computation, but it really is what we're going to use a lot. And it's used in conjunction with this complicated lemma, but it's not so complicated, but I don't want to go through the details of the proof of this one. So here we take a free sparse graph with a vertex of degree 4, and we look and notice this does not have any other degree conditions. So this is a bit more general. It doesn't need to be quite so general for our application, but this is the statement that they did in the paper. So here, we don't have degree constraints, but we do have constraints on this particular set. So V dash is the set of X in the neighborhood of our degree 4 vertex V, which have large degree, okay? And the constraint we put on V dash is we suppose that the subgraph induced by V dash is a complete graph. So it could be empty, so there could be no vertices of degree at least 6 adjacent to V, or it could be that there are vertices of degree 6, but they form a complete graph themselves. Under that assumption, Jackson and Jordan proved there is an admissible 1 reduction at V. Okay. So I wanted to give some indication for their argument, even though not doing the proof, because it sort of gives you the idea, I think. So you start with your vertex of degree 4, and let's suppose that it's not admissible. If it is, then we're going to be happy because we'll be done. But suppose it's not, then GVXY is not free sparse for some reduction. So we couldn't add this edge, which gives us a critical set. X in V minus V containing XY. And we have to think about where to go from there. So first of all, if Z and W are both in this critical set, then we would add 4 edges and 1 vertex. And so we'd find that I of X union V is strictly greater than 3X union V minus 6. So that tells us that at least one of these 2 vertices, Z and W, is not in X. Suppose it's W. So since W is not in X, we can consider an alternative one reduction at V, which deletes V and adds WY. So we could look at that one instead. Okay. But remember what I said about the degree in a subgraph induced by a critical set is at least 3. So the degree of Y is at least 3 neighbors over here. It's got 1 neighbor to V, so it's got degree 4 already. And now there's some other thing that's got to happen. It's going to have either an edge to W or it's going to be in another critical set. So suppose it was in another critical set like that, then it might have 3 here, or you might have to worry about how many of these ones were actually in the intersection of these two sets, etc. But you can see that it's sort of heading towards having degree greater than 5. It's good. If they were disjoint, it would be 3, 6, 7 already, and you'd be done. So somehow Jackson and Jordan were in a half a page, force it to be true that this is not critical. This critical set is an edge like this, or a small complete graph which pushes that edge there. Okay, so let's get rid of a bit of blue. So now we know that edge is there, and I've got a count of what, 3, 4, 5 already. So now there's no more, but in this case, they force Z outside of X, and hence they look at the one reduction, deleting V and adding ZY instead. And again, you get an extra edge there that pushes the degree of V of Y up to 6, which gives you a contradiction. So it's this kind of just locally looking at the degree that they do. I think I don't want to say any more about that. So sort of a sketch was written here, but it's really what I said. So you consider the one reduction for this YW, for the one vertex you had outside of you knew was outside of the critical set X. This gives you another critical set. You use some maximality argument to force this set Y to be a complete graph. And then you use an argument there to force Z to also be outside, and hence you end up with the degree of Y being too high. But I've said that a bit quickly, but I just recommend if you're interested to look at their paper, because it is a readable proof. I just decided for time reasons not to include all the details. So now I want to go through the proof of the theorem. So we know that every independent graph is free sparse. So we take a free sparse graph. We know it has maximum degree 5, minimum degree 4, and it's connected. And obviously it's free sparse as well. So we have one of these graphs with all these conditions, and we want to show it's independent in 3 dimensions. We're going to use induction on V again. We're going to use the 0 and 1 extensions. But because there were several conditions here, as well as free sparsity, we have to continue to be connected, continue to have minimum and maximum degree conditions. So to apply the induction, we have to check several things at each step. Okay, so it's easy to check graphs on most 4 vertices. They all have degree 3, so you can just do 0 extensions, say, to show they're independent. So we can assume that the graph has at least 5 vertices, and choose a vertex of minimum degree. So we need to know that when we do a reduction, we get a connected graph. So first of all, let's show that if we delete this vertex, then we'll get a connected graph. So suppose that's not true. Suppose we delete a vertex of minimum degree and we get a disconnected graph. Then it's true that each component is connected, obviously, but the minimum and maximum degree requirements apply to G, so they apply to the components. And because we deleted G was connected, and we had to delete a vertex to get disconnected, we do get the minimum degree in both, or however many parts we have, and we get the maximum degree for 3. So each component is connected with the minimum and maximum degree conditions, so it's independent by our induction hypothesis. So that's good. We deleted a vertex of minimum degree, so it had degree at most 4. Hence, it has degree at most 3 in any one component. So if I add V to any one of my components HI, the degree of V will be at most 3. And hence, we can use 0 extension to show that HI plus V is independent, as well as just HI being independent. Now, we can say G is independent because I take several, somewhere from 2 up to however many you like, independent graphs, and intersect them in a single vertex, V, then that union will be independent. And again, that's relatively easy. So we know the answer is true if G minus V is disconnected. So we can assume that G minus V is connected. Hence, if the degree of V, our minimum degree vertex, was at most 3, then G minus V is a connected graph with minimum degree at most 4 and maximum degree at most 5. So it's independent by the induction hypothesis. And hence, G is independent by applying a zero extension operation, which we already have seen preserves rigidity. Hence, we only have the one case to deal with, the degree 4 case, which is what the lemmas were for. So the previous lemma told us that there is an admissible one reduction at V, which will give us a smaller free sparse graph, G dash, and G dash is connected because G minus V was connected, and G had maximum degree D plus 2. So there is, so you notice when we do a one reduction, we add an edge over here. So the vertex, the degree of, say, that vertex goes down from D plus 2 at most D plus 2 to at most D plus 1. So we do have minimum degree at most D plus 1. We clearly have maximum degree at most D plus 2. So again, by our induction hypothesis, G dash is independent, and hence G is independent by our one extension preserves independence result. So that will complete the proof. Okay, I guess I went relatively fast through that if anyone has any questions. Okay, so then just to finish off, let me just again advertise that next week on Wednesday, Sean Dewar will talk about complete bipartite graphs. And then I believe on Friday, I will switch focus to global rigidity. Later in the course, we'll come back and talk about frameworks on the sphere and other things related to higher dimensions. But after Sean's talk, I'm going to switch the focus to global rigidity instead of rigidity to give you a number of lectures on that topic. So I will stop there and happy to answer any questions if you have them.
So by the way, some of us resolved that question of planar graphs being a matroid. It's not.
Oh, it's not?
Yeah.
So
Sean,
what's the example?
Yeah, so Sean noticed that if you have two triangulations or one triangulation and you remove an edge, there are only two edges you can move back to get a triangulation, either that same edge or the opposite one in the 4 cycle that you created. And then you can construct, I mean, it's pretty, I can just send you the file with an example, but yeah, and that was Sean's idea.
But yeah, you basically make sure that those 4 vertices are not connected by any edges in the other triangulation. And then there's no way you could do the basis exchange axiom. That's it.
That's a shame. Would have been a nice matroid. But...
No, yeah, it would have been a nice.
My first hint was I just Googled planar graphs as matroid and nothing came up. So
yeah.
Yeah, if it worked, someone would have figured that out, right?
Yeah, I feel like, yeah.
Well, I guess since we already know that they're not matroids, this is pointless, but I was just wondering, how would you even phrase the basis exchange question in that setting? Because you'd have a smaller triangulation and a larger triangulation, and I don't know, I wouldn't understand what you would be adding in the first place.
I mean, it's like the same as with a rigidity matroid, right? Like your ground set is just the edges of some complete graph. And so you would take 2 triangulations on the same vertex set and remove an edge from one, and then ask, is there an edge from the other that you can add back into this triangulation minus an edge to get another triangulation?
Yeah, so the smaller triangulation wouldn't be a basis, a base in this. Because you could always just, you'll have one vertex that's not connected to the rest by edges. So you need to throw those extra edges in some way to triangulate it.
Oh, okay. I see. Yeah, that makes sense.
So there are generalizations of matroids, right? So one is
either.
They don't work either.
No, because the thing that makes a greedoid not a matroid is not the exchange axiom, it's the second axiom. And this satisfies the second axiom.
Yeah, but there's more than just greedoids, right? So there's also delta matroids, which don't work because that generalization is saying bases can have different cardinalities, but that's not going to work. And there's polymatroids, but that's not going to work either. But so I guess I was going to say, well, maybe we can come up with some generalization of matroid that does work for planar graphs, and then play with that object, whatever it is.
But I think the basis exchange axiom is like the important part of it. If you just have a load of sets that are the same size, then you don't really have anything, I don't think. Unless you can weaken it somehow, but you weaken it quite a bit, because you're saying that sometimes you can, but usually you can't.
Simplicial complex. So,
Maybe go for something like that, yeah.
I mean, it is, but it is a simplicial complex, but I mean, that's a pretty weak. It's a pure d-dimensional or a pure 3n-6 dimensional simplicial complex.
Maybe you could say interesting things about the geometry of that complex.
Yeah.
So someone's saying triangulations of marked surfaces could be cluster algebras of finite type, but I don't know what they are. But
No, sorry, I don't know what cluster algebras are in any good sense to answer that one.
Maybe.
I don't know if any of the algebraists could jump in and comment there.
Oh, I don't really know anything about.
yeah, beyond my scope.
Oh yeah, so I'm curious now. So your independent sets are planar graphs in this potential matroid, yes?
Yeah.
Okay, so you take a independent set and then you take a subset of that. You're saying that there isn't always an edge we can add to the subset that would preserve independence?
So I think Daniel put a picture in the chat.
Yeah,
There's
okay, let me.
Yeah, so this is with basis exchange. So there are two graphs on the same set of vertices, both of which are planar. And if you were to remove the edge down the center in the first graph, then there were only two edges that you could add back to make it still maximal planar. That edge and then the other edge across that square.
Right.
And neither edge is a member of, neither edge is a member of the other graph.
It's a nice example.
Oh, so you've relabeled the oh, I was thinking one had to be a subset of the other. Okay, I'm combining two axioms here. Okay.
Yeah, and this was Sean's idea. In generality, I just wrote up a specific example.
Right, okay, yeah, that makes sense.
You've done it on 4 vertices, 6 vertices, so maybe it's true for like 4 or 5 vertices. I mean, it's gonna be true for 4 just trivially, so maybe 5 is not a problem either. But yeah, you'd have to pick very small triangulations to make it true, I think.
Oh, yeah, it makes sense though. You can take like just two radically different triangulations of a point set, delete one edge, and like you'll most likely not be able to add any other edge from the other triangulation. Yeah.
Yeah, that's the idea.
I can explain what I meant by cluster algebras if you're interested.
That would be
So there is some algebra, and in order to construct sort of a generating set for it, you write down a collection of seeds, and there's a nice combinatorial collection of cluster algebras where the seeds are these triangulations of a surface with marked points on. So for instance, if you've got this, I don't know, sphere, and you've marked points on it and you triangulate it, which are, I guess, the same as triangulation, like these maximal planar graphs, then there's this nice mutation thing that's defined in cluster algebras where you go from one seed to another you take the quadrilateral inside your triangulations with one line through it, and then you swap where that line is. So each line in your triangulation defines a quadrilateral, and you just swap it to get a new triangulation.
Yeah.
You go through, and all those seeds generate the same cluster algebra in some way.
So they're edge loops, aren't they? I think is what Bob calls them.
They're generally called diagonal flips.
or diagonal flips or something like
Yeah. But so you're saying the cluster algebra, there's like a relation between that and the flip graph of a
So when well, in order to find the generating set of your, like cluster algebra has a potentially huge generating set. In order to find a generating set for it, you have to do all possible flips. If you've got a marked surface, though, there's only finitely many flips that you can do, or only finitely many triangulations. So you get a finitely generated cluster algebra.
So do different marked surfaces correspond to Dinkin diagrams?
Yeah, you can start off with a Dinkin diagram and start doing flips, and start doing sort of, yeah. This is like one of the main things. There's like a classification of cluster algebras that have finitely many generators and finitely many finitely many relations. I'm not sure of the best way to say that.
Is
and
there?
some of, oh yeah, you go for it.
I was gonna say, is there a clean way in which a cluster algebra is a generalization of a matroid?
Not that I'm aware of, but it would be really cool if there was a link, I think. I've never heard of any link between them.
I've heard someone say once, and this was a while ago, so maybe the details wrong, that like the elements in like a basis for a cluster algebra are all algebraically independent. So it seems like maybe there's this larger matroid lurking, and then your generators are like certain bases, but not all bases. I mean, I don't know.
Yeah, that's it. So you start off with some like algebraic generators, and they're all algebraically independent. And to get the other ones, you do the rest of the generators are all Laurent polynomials in those set of generators. And yeah,
if you Google planar graph cluster algebra, you get a lot of things about cluster algebras that definitely say planar graphs in them. So it seems like there are connections.
Oh.
This is, I guess, now very unrelated to the lecture, but I have a question then. Do you know if there's like any relation between triangulations of lattice points and cluster algebras?
you mean by just Z?
Yeah, you could take like Z2 or like the triangular lattice or something like that. I guess you're talking about of surfaces, so I don't know how related it would be, but
I'm not too sure. Surfaces are nice because your triangulation, each edge is like a diagonal of a quadrilateral. So there's the important thing for a cluster algebra is the mutation. It should be something that takes you from one seed, and applying the same mutation should take you back. And
right. Okay.